Okay, we're going to be looking at the limit of a recurrence relation. Okay, now we looked at in class two different recurrence relations. One appeared to have a limit and one didn't. Okay, so now we're going to just explore when a recurrence relation has a limit. So for a recurrence relation, un plus 1 equals aun plus b, a limit exists where a is between -1 and 1. Okay, so if a lies between -1 and 1, there will definitely be a limit to the recurrence relation. Now that means it can't be as small as -1 and not as big as 1, so minus 0.999 would be fine. That would generate a limit, and so would 0.999, but if you were to try -1 and 1, you wouldn't get a limit. Okay, so it lies in between -1 and 1, but not including. Okay, so let's have that down. For a recurrence relation un plus 1 equals aun plus b, a limit exists where a lies between -1 and 1. Okay, so let's envisage a scenario in which we've got a recurrence relation that does have a limit. So if you think about a recurrence relation un plus 1 equals aun plus b, well, a limit exists when, well, what we tried in class is we got a result. I think the limit was 10, and then we hit the equals button again and we get 10. So a limit means that you reach a value, so the limit might be 15, so that might be un, and then you press the button again to get the next term, and the next term is 15 again. Okay, or you might, for example, have reached a limit at 23, and then that means you hit the button again to get the next term, and you get 23 again. Now what we can do is we can generalise that and say that that value that we've reached is L. Okay, so at some point we reach a value which we'd call L. Okay, now then what happens is we look for the next term, and the next term produces the exact same value, so we'd call that L. So if we've reached the limit here, let's say that that's represented by the letter L. So the next term after that is L again. Okay, now that makes sense because if we're calling the limit L, by definition, if we've reached the limit, you get the same thing again. So L is then followed by L. So what we've got then is L equals AL plus B. So it's just like that scenario in which I said if the limit was 23, okay, so the previous term would be 23. And then the next time after that would be 23 again. Okay, so we generalise that and say that the limit is L. So the limit's L, and then the next term after that is still L. L equals AL plus B. Okay, now let's just put this straight into an example. Example 1. Okay, so example 1, we're going to find the first 6 terms. And the limit of the recurrence relation un plus 1 equals 0.6 un rather, plus 12, and we're told that u0 is 20. Okay, so the first bit is familiar territory, that's what we did today. Okay, so if u0 is equal to 20, we need to get up to u6, so u1, let's do the working for the limit, that would be 0.6 times 20 plus 12. Okay, and that will give me 24. Okay, then we look for u2, so we do the working again. Remember, show the working twice. 0.6 times 24 plus 12. Okay, and that will be 26.4. Okay, now the calculator now recognises the reconciliation. I've shown the working twice, and I can now just start hitting the equal sign. So the next one, u3, will be 27.84. And then hit the equal sign again for u4, 28.704. u5, 29.2224. And finally u6 was the sixth term I was looking for, 29.53344. Okay, that's that bit done. Okay, the next bit of the question asks me to calculate the limit. Okay, now the first thing, is there a limit? Well, there is definitely a limit to this question. And the reason being is because, as you can see, the value of a lies between -1 and 1. So a limit exists. Let's take this down. A limit exists since a lies between -1 and 1. But let's put it in context, the number is 0.6, because 0.6 lies between -1 and 1. Okay, so that's just a wee one marker. That's why we know a limit exists. Okay, now in terms of going forward to find the limit, okay, so what do I know? Okay, if I reach the limit here, the next term after that will be the limit again, because by definition that's what would happen. If you've reached the limit, the next term after that is still the limit. Okay, so L equals AL plus B. Let's now put numbers into that. So that's L equals 0.6L plus 12. Okay, so that's just throwing that in. I've reached the limit, and then the next term is the limit. So the limit equals 0.6 to the limit plus 12. I can then bring that over, change its sign, and that will be L minus 0.6L is equal to 12. That's now 0.4L equals 12. And then L equals 12 divided by 0.4. Don't reach for the calculator there, that's an uncalculator question. It can be easily executed without a calculator. Multiply top and bottom by 10. And that will give me 120 divided by 4. The limit's 30. Okay, let's try example 2. Okay, question 2. So a sequence is defined by un plus 1 equals 0.4 un plus 8. Okay, so first question is, does it have a limit? And it's yes, since 0.4 lies between -1 and 1. Okay, next thing we're going to calculate the limit. So remember, if we're to reach the nth term and that's the limit, then n plus 1th term is the limit again. So it's L equals AL plus B. Let's put that in the context equation. L equals 0.4L plus 8. Bring that across. L minus, change side, change sign. L minus 0.4L is equal to 8. 0.6L is equal to 8. L is equal to 8 divided by 0.6. Multiply top and bottom by 10. And that will be 80 over 6. Okay, so that won't give me a whole number, but I can just leave it as a fraction. I could divide top and bottom by 2. And that will give me 40 over 3. Okay, let's try an example 3. We're going to calculate the limit again, given un plus 1 equals 0.un plus 2. Okay, L equals 0.9L plus 2. Bring that over. L minus 0.9L is equal to 2. The limit, take away 0.9 lots of the limit, gives me 0.1 lot of the limit, that's equal to 2. L is equal to 2 divided by 0.1, top and bottom by 10. And that will give me 20 over 1, and the limit is equal to 20. Okay, so you're going to try this one, calculate the limit. There's A, L equals AL plus B, and take it from there without a calculator.